then it's Cotogen bundle as a natural symplectic structure. So it was either minus or plus d lambda, where lambda is a Liouville form, which is canonical. And so that, in fact, if you have a diffeomorphic manifold to M, so this is, let's say, a fact, this implies that the Cotogen bundle are symplectomorphic. So that means that indeed let's write it this way. The symplectic class of T star M is an invariant, here I mean up to diffeomorphism, of the manifold M. So that the reverse question that Uppsala said is, does this invariant determines the smooth type of the manifold M? So we don't know in general, but there are some results. Maybe I can recall them. So, for example, result proved by many ways and many people. Let's say Viterbo. So Viterbo, Solomon-Weber, and Abandon-Schwarz, they showed somehow that let's say at shape for Hamilton and Fleur homology of a contingent bundle of M is somehow isomorphic to the singular homology of the free loop space of M. So that means we get some homotopy data from the symplectic structure of T star M. And we can even have better, as there is another theorem.
Excuse me, are you using omega for free loop space?
I mean, okay, so maybe.
Yeah.
L.
Really?
If you use this symplectical mod, can you bound off that? Local mod. It's local mod you create Hamiltonian, but it's symplectical mod.
And so another result of Abu-Zaid is that we can distinguish, let's say, exotic S4K plus 1 sphere thanks to holomorphic curves in T star M. So that the question of is it a full invariant is still could still be possible, and at least for closed manifold. Now, what we'll talk about is a relative case.
Technically, he doesn't use holomorphic curves in the cotangent bundle. He embeds the cotangent bundle in a larger, non-exact symplectic manifold and uses curves there.
Oh yeah, okay. So let's say it's by holomorphic curve techniques. Then.
Maybe it's relevant to say, just maybe add VP somewhere.
Yeah.
Just,
What? What?
he just really is able to tell you whether the thing's in VP or not. Or
Unparallelizable.
He didn't say distinguish all exotic spheres.
well,
Some.
Some.
I mean, it's just motivation. And so the relative version is now you take some submanifold, let's say, of dimension n, and now what you can do is, as said Uppsala, we can build the conormal. So let's say so we can do two versions of this. As we said, there is the cotangent bundle, which is naturally associated to M, and in there we can build Ln, Lagrangian submanifold, and so it is defined as the set of covectors above the mid submanifold n, such that this covectors vanishes on all tangent vectors to the manifold n. So that basically these are the covectors whose kernel contain the tangent vector to n. So if n is indeed embedded, I mean, so what I said, Ln is so n minus m vector bundle over n, so that it is indeed of dimension n, and we can show that it is Lagrangian, in fact, because if you take I don't know, let's show n is exact Lagrangian. So if we take tangent vector to Ln, we can send it to the base projection restricted to n. We have This tangent vector, in fact, is a tangent, the image, the projection of the tangent vector W to the conormal is a tangent vector to M, and by definition of the Liouville form, you have so the Liouville form above a covector U, it's exactly U evaluated at the projection of the tangent vector. And by definition of U, this has to be 0. So that we have omega equals 0 and lambda equals 0, so exact. And we conclude from this, seeing that if n is isotoped through smooth embedding, then Ln is isotoped through Lagrangian by Hamiltonian isotopy, and so that we have a new invariant of n. So the Hamiltonian isotopy class of Ln is an invariant of the smooth isotopy class of n in M. Now we can reduce the dimension of Ln, because it is obviously non-compact, by passing to the unit cotangent bundle. So this is Lagrangian version. So as you know, ST star M can be seen as a submanifold of T star M if we fix some Riemannian metric, for example. And in fact, it is the boundary of the Dix tangent bundle, so that are which is so it's a boundary of a Liouville domain, and the radial vector field. No, I'll just say it. The radial vector field is Liouville vector field for this hypersurface in T star M, so that the symplectic structure here gives the contact structure on ST star M. Let me just write this. So lambda restricted let's say k lambda maybe. Is contact. And now we can just take the intersection of the conormal bundle of n with the unit cotangent bundle to get the unit conormal bundle of n, which now will be compact submanifold, close compact if n is close, of the unit cotangent bundle. And basically, which is defined by the same thing with the requirement that the covector U is of unit norm. And what more can we say? Now this is Sn minus m minus 1 sphere bundle over n, so that it is of dimension n as the m minus 1 plus n. No, okay, so other way. Dimension m minus 1 in st star m of dimension 2m minus 1. And it has to be Lagrangian because it's a boundary of Lagrangian, or a boundary or notation of the Lagrangian ln in the complex hypersurface st star m. So it's Lagrangian. And obviously we have the same fact. It is the class of lambda n is an invariant of the smooth class of n. And there is no problem with the choice of the metric here because in fact we can do it without choosing any metric, considering in place of st star m, let's say this as a remark. In fact, st star m is contactomorphic to I need to write it. Okay, maybe this way. To the oriented projectivized cotangent bundle.
Sorry.
Wait.
How do we define contact form on oriented projectivized cotangent bundle?
You get this is a quotient of T star m, and you can check that the Uville canonical form, which is PDQ, some other PDQ, in fact is is proportional on some if you take a covector, a line of covectors, you have to check that you define the same hyperplane on all of this. So let's say R plus U. We want oriented.
The kernel
This is
of PDQ is the same as the kernel of line.
yeah, kernel of PDQ instead of kernel of PDQ multiplied by some strictly positive number.
Okay, so yeah, what I really wanted to say is that it seems that the contact form is really literally the same on the left and the right hand side.
There is no contact form here. I mean, because this is only you see on the line. It's not well defined. It has to be multiplied by some number. So here we only have really an hyperplane field, but which is the same as this one because you see that this one is just the hyperplane field in the one slice, and so it's okay for this.
Yeah, I'm very confused. What's the definition on the right? P plus? What does it mean? It means you take the fiber.
It means you take the quotient. Okay, I write it. By the R plus R strictly positive action. So on fiber. So multiplication. What?
Also, it's the cotangent bundle minus the zero section. Right?
But it's
yeah.
it's your
All right.
first
Yeah.
method.
That's something. Let's.
Yeah, the other one you put all for the question.
Yeah. Otherwise, it doesn't make sense.
Canonically.
So it's a zero section. Okay, but so this is really an interesting definition of the unique conormal bundle, and so that really its class is invariant, at least in this. And this isomorphism is canonical from the moment you fix a metric. And the advantage of having a metric is that you can identify T star M and the cosine bundle and the tangent bundle, so that by the simplification, so let's say, yeah, Ln becomes, so the conormal bundle becomes the normal bundle. Okay, maybe it's not. No, to write it. Let's say normal bundle to n. And so that we can really picture what's going on. Let's say for the trivial case when I can draw, so dimension of n is 0 and dimension of n is 1. Then, for example, you can get something like this. This is m. It's tangent bundle. Let's see. A direction like this. You have the unit tangent bundle here and here. And if we take n to be some points in M, some embedding, then the ln is the conormal fibers, and its intersection here is the unit conormal bundle. And we can see that this is the same as, topologically as the normal bundle, because we can identify, so in M, and N, you see that the normal bundle to N can be seen as a tubular neighborhood of N in M. And the boundary of a tubular neighborhood can be identified with the unit conormal bundle, so that this is really on the N. And we see the 4 points. Now, I maybe do a more interesting example that's this dimension. So let's proceed to maybe the example of Arnold, which are plane curves. For my definition, there is nothing interesting in plane curve because I only talked about embeddings. But in fact, we can define this construction for immersion. So just let's say remark lambda n is well defined for n only immersed in M. And the thing that can happen is that lambda n could have double points because of because if we see an example, so this
sorry.
Yeah.
A plane curve is an S1 immersed in the plane, right?
Yeah, the curve is this, but for now my definition was only for embeddings.
Okay.
So I just have something to say about immersion, to say it's okay. And the fact is, lambda n is embedded if n is self-transverse. Why? Because over double points, so for example, over this double point Q, we have 4 points in lambda n, so there is let's call so there are basically you see that there is two normal coming from this part of the curve, so this normal in this way and the other way, and two normal coming from the other way, so that you have something like, let's call it TQNN plus TQNN minus TQN. So let's say the orthogonal of this point. So you have both normal vectors with in two sides and the other two. And in fact, this has to be different because these 2 points are obviously different. And if if a point in S T star M, so call it U, represents TQ when N let's say plus minus n tq to n, then it has to vanish on both planes. But this is not possible because then it would imply that U vanishes on the sum of these. And as we assume that this is self-transverse, this is TQN. And so as this is a non-zero covector, it cannot be zero. And it implies U equals 0. So that in fact there is no problem for self-transverse immersion. And there is something more for the case of plane curve. As you see, as I said, you can identify the unit normal bundle with the boundary of a tubular neighborhood. And here you see that in the case there are two connected components. I mean, locally, and in fact, the question is how these two connected components will know each other. And if you think a little bit, you'll see that each of these components correspond to an orientation of the tangent bundle to the circle. So that in fact, what we are defining is two cover of n, which is exactly the orientation cover. So that we have say proposition. So if n immerse in M of codimension 1, so n equal m minus 1, lambda n decomposed into, there are two possibilities. If n orientable, then lambda n, which is the orientation cover, has to split into two components. And otherwise, it's connected. And so, in the case of plane curves, as a circle is always orientable, we have this situation occurring. And so that there is something more to say, is that in this case, basically lambda n plus and lambda n minus, they are the same information because they are obtained by antipodal action on the cotangent fiber. So basically, you for a point here in the unit normal bundle, this is a point, for example, of lambda n plus, whereas this one is a point of lambda n minus. So that really, we can only keep lambda n plus. And this is an advantage because now so still in this case, n is allowed to have inverse self-tangencies. That is to say, at a point yeah, it's okay. So you see here that if I draw some orientation and the co-orientation, here the co-orientation of the two sides differ. And in fact, over this double point, lambda n is embedded. Because one point corresponds to plus this side and one point to plus this side. So there is really two different points. And that is what allowed Arnold to build invariants of plane curves up to regular homotopy, let's say without the direct self-tendencies, because then the only problems, the only double point of lambda n plus occurs at a direct self-tendency. For example, if you have a front like this, a plane curve like this, okay. Here, if you have this co-orientation, here you have the same, and if you try to cross this one to go to this, in between these two, and then as a non-embedding moment. So that basically, these are not the same Legendre isotopy class. And okay, so what can we do for plane curves? For example, we can define the invariance of lambda n to be invariance of the plane curve. So alors, what do we have for lambda n? It is a Legendrian, let's remember, it's a Legendrian torus in, no, not torus, it's a Legendrian circle, so in fact it's not, lambda n plus, in is T star R2, as is R2, And so the resonant knot has classical invariance. So okay, so obviously there is this smooth knot type. Here you see that this manifold, which is basically a trivial bundle, is not simply connected, so there is in the smooth knot type there is the homology class of lambda n plus. Which is basically the winding number of the plane curve. And you have the rotation number and the first unbanker. And then, what I will tell you now, non-classical invariant. How do you compute this? You should have a way of seeing this knot, and as you know, a usual way to see the knots to have their front. But here we are not directly in the position to see the front. So in fact we will have to identify this bundle with a one jet space. So I said also Uppsala about knots. So here it's the one jet space of S1. And they are contactomorphic. And this map, basically, in coordinates, so R2 cross S1 coordinate Q P, where P is a unit vector, and you have to associate something in J1 of S1, so this is. Yeah.
What exactly are you now defining rotational source of banking?
Rotation number of lambda n plus.
Rotation number.
And yeah, it's there are the classical invariant of this Lagrangian knot, in fact. And so you can see. So this is the way, and this contactomorphism is given by, so it's a bundle map over S1, so we keep the unit direction. And here, you have to keep, maybe I write it and explain. Okay, I'll explain on the curve. So this is the z direction, so the, where there will be the front, and this is the cotangent direction of S1. So that this is basically if you are at some point here, you can decompose Q, so this is Q, in a part along the, okay, maybe this example, and let's say this is P, you have to decompose Q along P. So something like this. So this is Q RPP. And then the remaining part, which is the tangent part, is this. So and so what interests us is only the front projection. So we only need to understand the map. So it's basically a phi, the front projection followed by this map to QP div P Q scalar P P. And
Anton, why do you put in a P at the end there?
oh yeah. Yes. Okay. And if I do this for these two examples, we get, let's begin with this one. So we get a front in S1 cross R. Donc I will draw it as, so this is 0 to pi, this is S1, and this is the Z direction. And in fact, here, if you take, for example, this co-rotation, you see that, and here's the origin, the vector Q is always in the direction of P, so that its scalar product with P is the radius of this. So we'll get a really simple front, which is, here we have the radius of the circle. Whereas for this, this is the zero section. There is, you see that the co-orientation, there are some points which are never attained in the circle, and there are some double points. You see that here there are 2 points with the same co-orientation. So it means that there should be double points over the same point. And in fact, you see that here at the inflection point, so it's something like this. Here the co-orientation is rotating, and at some point it stops rotating this way and rotates the other way. So it means that there must be a point when we get back. So basically it's a cusp. And we have the same thing on the other inflection point. So we must have 2 cusp points, one in each way, and something growing and decreasing with over n, so that we get, in fact, the TB minus 1 and mat. And now we can compute all the classical invariants here, and we distinguish them, for example, here is distinguished by the winding number, but Thorsten Benkin will work too. And now, to finish, I will say that these are not enough to distinguish plane curves, at least oriented plane curves, and we can use Legendre contact homology of these knots to distinguish them. So here I have an example of Lenny. So this is a plane curve with self-transverse intersection, and according to which rotation you put on it, you yield 2 different Legendrian knots. Here they are their fronts. So it's basically, you see a knot which is linked. And this can be distinguished because in fact they are not exactly, but you can link them to a Eliashberg knot, or I don't remember which is which. Or maybe it's not that important, but it's 2 different Eliashberg knots that are distinguished by the Poincaré polynomial. I finished here.
there any questions for Antoine?
This last thing which you
Yeah.
with the contact homology, is there any connection of this with the classical invariance of Arnold for
Classical invariance of?
Arnold defined some special invariance of plane curves.
Yes, obviously.
So what is it?
In fact, the invariant of Arnold, they can all be deduced from this one. You see, because I mean the local invariants are G plus, and basically this is something which counts the number of direct self-tangency between two plane curves. So it means that, as I said, a direct self-tangency is forbidden. So when there is one, you change the Legendre entropy class of the conormal knot. And it's found out that this is basically the first Benquin plus the winding number, so let's call it n, minus 1. And there are two other invariants which are basically G minus is the same thing, but for I'm not too sure about G minus, but I think we can get it from the framing. And these two invariants, in fact, they only depend on the frame knot type of the Legendre knot. So that in fact, Arnold invariants are not really Legendre invariants, they are only frame knot invariants. So yeah, so here it's something that Arnold couldn't have seen with these invariants. Yeah?
You can define a conormal for something with a cusp in the projection, right?
Yeah, you can. Yeah, I don't speak of it, but that's what Arnold does when he looks at fonts of plane fonts, and you can even do it for like strange fonts like this, which are not co-oriented, because you see here if you follow the co-orientation here, it has to go there, then continue as a cusp, and you go to the Olbers co-orientation. So that in this case, the conormal will be connected. Yeah. And so there's something to see from the first Benquin of this, and it's still a Legendre knot.
So if you take a front of a Legendre and you apply this construction,
yeah.
do you obtain anything meaningful?
Yeah, any friend in the conormal is also a friend. I mean, any jet space friend is also a conormal friend because you can embed. It's like you stretch the R into a circle.
From another perspective, one can say, okay, any Legendre inside unit cotangent bundle, perturb it generically, and then you get what is a front projection. That's the Legendre front projection in the base, and that determines the Legendre. But of course, that has some singularities. In this dimension, it's sections and cusps, and high dimension it's more and more.
Maybe it would be nice in the 8. So take the 8 in there.
Yeah.
Do over the Meister 1, for example, on the right.
Yeah.
Good.
Okay, but then.
And then apply the move that you explained 2 blackboards ago, and you'll get the green guy.
Yeah.
Yeah, so in particular, if you start with the Legendre knot, the front of a Legendre knot in normal R3, so you can think of that as now giving you a curve in R2.
Because
and I think the conormal of that is the same as the original Legendre knot in a Darboux ball inside of the one jet space of S1, I think.
there is no inflection point.
because the total binding number is 0.
Is that right?
I think there's maybe issue with
You
this.
see this one is the front of this one, or what?
Yeah, this
If
is
you
the
start with
same.
Legendre
This is
in
equivalent to
R3,
the front of that. It's very much.
you can set it up so that,
Seen in J1.
Ah, yeah.
so just.
Okay, so it should do
Oh,
something.
then you
Yeah.
think of it in the.
Now clear some
I'm just saying, like, if you take the 2 5
Right, do something like really.
in the plane,
So-
that is actually.
Just you will do something like. You see this point?
Okay, right.
But
It's
then what
here.
you said is right, if you take the
It should do
the
something
far
like
right from
this.
zero, right,
Yeah.
it just looks like the standard cotangent bond.
On the front
Piece
to add
of
this
front.
relation.
That's how it's done.
Because you see, the coorientation doesn't do something. Instead of
It doesn't
I mean,
want
that-
going
this is-
this, it is going to do something like this.
Yeah.
Ah,
This
maybe.
curve is.
Yeah, maybe it has to. Yeah, you think do something like this? No. But there is.
chances.
Well, maybe we can continue this discussion. So we'll come back at 11:40.